check. You put in your pocket.
Does it work?
Yeah.
All right. Hi, everybody. I hope you have a great time. We all have a great time. I'm pretty sure we'll do. So what I'm going to do, I'm going to start very basic through like standard, basic cosmology, so everybody's on the same page, describing homogeneous and isotropic universe. I'm going to go a bit fast, okay? But of course, you ask me questions if something is not clear. And then we'll get into the real reason I'm giving these lectures is to describe how the structure in the universe forms. And so I'll start by discussing a bit of the math that we need to describe fluctuations. What is a random field, particularly what is a Gaussian random field, what are correlation functions, the power spectrum, and so on. And then we'll get into the physics of how structure forms, okay? So that's kind of the strategy for today. So I'm going to start with what I call the smooth universe. And the idea is the universe, if you look at the sky, is not smooth at all. Okay, so the galaxies are clustered, all sources are not randomly distributed on the sky. But if you average over very, very large scales, okay, the universe becomes smooth in the sense that the number of, say, galaxies on this part of the sky, when you average over large scales, or on that side, they become the same as you average over very, very large scales. And so we start with this assumption that underlying everything, we can describe the smooth part of the universe averaging over very, very large scales as an homogeneous and isotropic universe. And here we are following on the steps of Einstein, who started with this assumption without actually zero observational evidence at the time. Okay? Now we have extremely good evidence that the universe is homogeneous and isotropic, which I'm going to abbreviate like that. When you average over very large scales, and we have two evidences for this, the distributions of galaxies themselves, and we're going to quantify this later in a more precise way. So the deviations from homogeneity and isotropy are going to be described by correlation functions. And technically what this means is that the correlation functions at large scales will go to zero, okay? So there will be a quantitative description of this. And the microwave background is also homogeneous and isotropic. So we are going to abbreviate microwave background as CMB. So what is the microwave background? The microwave background is a remnant of the early universe of all the photons when the universe was dominated by radiation. That radiation is essentially becomes is a thermal, to an excellent approximation, is a thermal black body, and it cools down after the universe roughly of an age of 300,000, 400,000 years old. This cools down passively since then. And so when we look, if you look at the sky with microwave glasses, you will see that it's a bath of uniform temperature of 2.7 degree Kelvin, and it's the same in all directions to 1 part in 10 to the 5, okay? So this is sort of at the level of 10 to the minus 5, that is isotropic everywhere you look. The distributions of galaxies, when you look at very, very large scales, we will see that to the level that we can measure, more or less, correlation functions at the largest scales are of order 10 to the minus 3. And eventually, as we keep measuring larger and larger volumes, this number should be going down and down. Okay? For the CMB, because we already see the whole sky, we already have the number. Okay? So So this justifies describing the universe as an homogeneous anisotropic background, and on top of this, we are going to put the fluctuations, okay, which describe the structure. Now, what does this mean? Of course, the description of the universe as a physical system is done through general relativity. So these observational results carry to general relativity as a description that we are going to have a 3 + 1, the composition of the metric, 3 spatial dimensions and 1 time. Okay? And what we are going to do is we are going to slice space-time into these spatial slices, and each of these 3D slices satisfies the symmetries implied by this homogeneity and isotropy, okay? So homogeneity, it means that all points in that slice are equivalent. And isotropy means all directions are equivalent. Okay, so isotropy means invariance under rotations. So if I sit at a point and I look at any other direction, they all look the same. Okay, especially say the temperature of the CMB will be the same, okay, or the number of galaxies will be the same. Okay, and then homogeneity means invariance under translation. So if I look at what's going on at this point and I do a translation, the physical properties are the same. Okay? So this will be translation invariance. This will be rotational invariance. So each 3D slice satisfies these symmetry properties. Okay? Now, luckily, you know, if you remember some GR, one of the main lessons of general relativity is there is general covariance. You can choose the coordinates you want, right? And you can always choose the coordinates in such a way that these properties are not really obvious, right? For example, if I have the CMB temperature as the universe is cooling down, so here is 10 degrees at this slice, okay? And then here is, at a little bit later, is say 5 degrees. You can always slice the space-time in such a way at an angle so that in that slice, the temperature will not be uniform. But that will be making your life complicated unnecessarily, okay? So the next thing is the universe comes with a clock, which is the CMB. So it comes with a natural slicing, which is the CMB temperature. You can think of it as a clock. So essentially, you can choose your equal time 3D slices as the slices where the CMB temperature is uniform. Okay, so in practice, that's what we do. And we introduce a set of fundamental observers, which are at rest with the CMB, okay? And we call those observers the co-moving observers. And so these co-moving observers, at each 3-dimensional slice, they set coordinates, and we call those coordinates the co-moving coordinates. And so in these co-moving coordinates, you can choose, you can choose them to be Cartesian, spherical, and so on. So I'm going to choose typically spherical. So it will be a radial coordinate chi and 2 angular coordinates phi and theta. And just from these symmetries considerations alone, you can write the metric of the space-time just from symmetry alone. So this is just using isotropy of the 3D slices. So these comoving observers, we carry clocks that measure cosmic time, which we call T. And then you will have the spatial part of the metric. Okay, which can have by an overall function of cosmic time, A of t, which we call the scale factor.
A squared.
Yes, thank you. And then just from the considerations of isotropy, this is the angular part of the metric, and this function is fixed by as up to a constant by the assumption of homogeneity. So this function, sigma, depends on spatial curvature. And the spatial curvature constant k can be positive, negative, or 0. And so in that case, you will have different functions of spatial curvature. So this tells you what is the spatial curvature of each of these slices. Okay? As I'll get to in a second, there is excellent constraints on the spatial curvature that constrains us to be in a spatially flat universe. Okay? I'll quantify this in a second. So for a few more minutes, I will keep it general, but very quickly I'm going to set into the spatially flat case. So you can also write this. So this is the Friedman, Lemaitre, Robertson, Walker metric. You can also write it in a slightly different form, which is something we are going to use. So you can write the space-time interval using specifically this parametrization, which is totally equivalent to the one I just wrote. Okay, the omega square is the angular part of the metric. And again, comoving observers have constant comoving coordinates. In both parametrizations. And something we are going to use quite a bit is to, sorry, I keep forgetting the square here. Something we are going to be using is that is very convenient when we write equations of motion is to introduce a conformal time. Okay? So you can see here the spatial part of the metric gets multiplied by the scale factor square. We are going to define a new time variable, which is conformal time, which I'm going to call tau, so that the whole space-time interval is just an overall a square times the metric in these conformal coordinates. Okay, so we are going to use, in the equations of motion that I'm going to write, once you do this, because a squared enters an overall factor, the equations of motion simplify in this conformal time variable. Now, you can see that any physical distance, so this will be the distance squared part of the metric, okay, gets multiplied by a squared. So that means that any physical distance in cosmology is a co-moving distance multiplied by the scale factor, and that's essentially where the name scale factor comes from. And you can think of it as any physical distance between two objects that are being stretched by the expansion of the universe. Okay, so this describes the expansion of the universe. And this defines the co-moving distance between 2 points. Okay, and so it's going to be very convenient to write things in all distances in co-moving coordinates, and you can scale it by the scale factor at any time that you want. Okay, so that's the usefulness of working with co-moving coordinates. Now, once you have that, you can see easily by taking a time derivative that is anything that has constant that is not moving, so it has constant co-moving coordinates. Okay, so for example, I paint somewhere in the universe, and I take one galaxy and another galaxy, assume the galaxies do not move, they just participate only in the expansion of the universe. As time goes on, these galaxies are going to be farther and farther apart, which means there is a relative velocity between them. And just by taking a time derivative from this, with respect to cosmic time, you see that the relative velocity between any two objects at constant co-moving coordinates is all coming from the time derivative of the scale factor. Okay? And I'm using derivatives with respect to cosmic time, t, as a dot. And we can rewrite this as a dot over a times the physical. And this defines what we call as a Hubble constant. Okay, so h here is the Hubble constant, which is not a constant. Don't blame me, that's the name. So it's a constant at a given time, but it's not a constant, so it's a function of time. It's only a constant if the universe is dominated by a cosmological constant, as we'll see in a second. But this is what we call the Hubble's law. Okay, so the relative velocity between two objects is proportional to the distance, and that constant of proportionality is called Hubble constant. Okay, and the value of this Hubble constant, the fact that this is positive tells you the universe is expanding. And this is essentially how the expansion of the universe was discovered. If there is a relative velocity between two galaxies, okay, moving away from each other due to the expansion, means I'm going to see essentially a Doppler shift of galaxies moving away from me when I look at the spectral lines. And this is how we, in 1929, Hubble, and with many other contributions of other people, obtained that the universe was expanding. The value of this Hubble constant today, so quantities evaluated at today's time, I'm going to use the standard 0 as evaluation at current time. So usually it's written in these weird units. So the value of the Hubble constant is written as 100 little h, where little h is roughly 0.7, okay? So we'll get to discuss a bit more of that later. But you see, this velocity over distance has units of 1 over time. So the Hubble constant has units of 1 over time. But because we measure velocities in kilometers per second and cosmological distance in megaparsecs, you can see there are two distance units here that cancel and has units of 1 over time. The reason for writing it in this very strange way, 100 times little h, has to do with historical reasons. There was a big uncertainty on this number back when I was a student, or even before. People were arguing it was between 50 and 100, so this was between 0.5 and 1. Today, we argue whether this is 0.72 or 0.68. So we're still arguing about the value of the Hubble constant, but now with a much smaller deviations. Now, because this is, remember, the Hubble constant tells you the expansion rate of the universe, right? It's a characteristic timescale, is 1 over the Hubble constant. Okay, so that's what we call the Hubble time. And from here, we can define a characteristic length scale, which is the Hubble radius. And this essentially tells you what is the size of the observable universe. Okay, where the Hubble time takes you essentially what is the characteristic time that it takes for the size of the universe to double, essentially. So this is a very important length scale because, as you'll see, it appears in the equations of motion, okay? Because these are just local time derivatives of the scale factor. Okay, so once we have that set up, as I mentioned, we know the universe is expanding by looking at how the light redshifts gets redshifted. So let me remind you of the concept of redshift. So if I have a source emitting light at some particular wavelength, this light propagates. And at a later time, there is an observer here in another galaxy with a telescope. And because the universe is expanding, the wavelength of light gets stretched as the universe expands. So this observer receives the light at a different wavelength, lambda observer. Okay? And the ratios of this is, of course, the ratio of the scale factors at a time. So this observer observes at t observe, and this emission happens at time emission. And so this defines the concept of a redshift. Typically, we set the scale factor is a function whose overall size we can always absorb. So the convention in cosmology is to set the current scale factor equal to 1, okay? So then there is only one A of t, which is what was A before, okay? Which will be smaller. And so usually we say A of t is 1 over 1 plus z. So if you look at back in time, so today we are at redshift 0, the scale factor is 1. As you look back in time, the redshift is higher and the universe was smaller, okay? And so here we are taking advantage of the fact that looking through the universe is like looking through a time machine, because light travels at a finite speed. The farther away you look, you're looking into the past, because light takes some time to get to you. The same way, when we look at the sun, we are seeing the sun as it was 8 minutes ago. As you go farther and farther into the cosmos, you are looking back into earlier and earlier times. That's just from the fact that the speed of light is finite. Okay, so now how do we put this together into general relativity? Everything I said until now is all from the symmetries, okay? Without using any equations from general relativity. This is true for any metric theory of gravity. So now we're going to get a bit more specific. We describe the smooth universe as a perfect fluid with some density, which I'm going to call rho, and some pressure, which I'm going to call P. And because of homogeneity and isotropy, this can only be functions of time, okay, at the time of my slides, where the temperature of the CMB is constant. And the right-hand, the source of Einstein equations is the stress energy momentum tensor. So we are not going to use this a lot, or not that much at all, but just to be complete, you can write what is the stress energy momentum tensor that acts as a source of Einstein's equations in terms of the properties of the fluid and the forward velocity of the fluid. Okay? Now, conservation laws are very important, and in general relativity take the form of the covariant derivative acting on the stress energy momentum tensor vanishes. And for this very simple metric, okay, describing a smooth universe, this is a trivial, looks like a very fancy equation, but it's actually very trivial. It's no other thing than the first law of thermodynamics, describing that the time derivative of the energy, so you can think of rho as the density, energy density of or mass density, okay, since we are taking speed of light equal to 1. So this is energy density times the comoving volume, right, A cubed, okay? So this is the energy, time derivative of the energy is minus P d volume, okay? So this is just the first law of thermodynamics for a fluid that conserves entropy, okay, which is an ideal fluid. So, you know, we don't need much general relativity to understand this, okay? This is very simple. The universe is expanding, and the pressure is doing work, okay? And then you satisfy the first law of thermodynamics. Now, the interesting thing is that from this alone, and the equation of state of the fluid, we can derive how the density depends on time. So the next thing I'm going to introduce is the equation of state that relates pressure to density. And it turns out in cosmology, we are very lucky because this equation of state, a linear equation of state, where the pressure is proportional to the density with a constant that we call W, describes most of the observable components in the universe. Okay, so W is known as the equation of state parameter. And we have, by using, as a first exercise, you can show, I'll give you this exercise, plug in this here, then you have an equation for rho as a function of time, or rho as a function of the scale factor, and you derive from here that necessarily the time dependence of the density on time is through the scale factor as A minus 3, 1 plus W, okay? So that's the first exercise you can do. And let's take some examples. So the first example is what we call matter, or non-relativistic matter. So non-relativistic matter has W equal to 0. That may sound strange, okay? So if you have non-relativistic fluid, it means that the velocities are moving at velocities which are much less than the speed of light, right? And if you think about the units, pressure actually has units of density times velocity square. So actually, what it should be here, there is a c square here that I'm setting equal to 1 because I'm working in speed of light equal to 1 units. So for a non-relativistic matter, the pressure is typically of the order of rho v square. which you can always say this is rho v squared over c squared times c squared. So you can see now that the order of magnitude of this guy is v squared over c squared, and if it's non-relativistic matter, this is a very tiny number, okay? So we set it to 0 as an approximation. So in that case, raw matter dilutes as 1 over a cubed, and this should be intuitively obvious. So if you have matter which is non-relativistic, this matter, as the universe expands, it dilutes as 1 over the volume, okay? And the amount of energy you have is just the rest mass of the particles. And so the energy density goes as 1 over a cubed. If you have radiation, like photons or any massless particle, then this W constant is 1/3. So raw radiation goes as 1 over a to the 4th. Again, this should be also clear why you get this. You got a 1 over a cubed dilution due to the effect of the volume, and you get an extra 1 over a compared to here, because as the universe expands, the photons are redshifting, okay? And so the wavelengths are decreasing as 1 over a, and so the energy is decreasing as 1 over a, so you get an extra 1 over a dilution. Finally, if you have some weird equation of state, we have very good evidence for something called close to what we call a cosmological constant, which has an equation of state where W is equal to -1, which means a negative pressure, which means tension, okay? Like I say, a rubber band. So rather than positive pressure, you get negative pressure. The weird thing is relativistically negative, so it's a very strong negative pressure. And in that case, you can see if W is -1, then for this cosmological constant, the energy density actually doesn't dilute at all, okay? And so that means that at late times, as these things dilute, this may come to dominate. And this is exactly what we see, that in the last few Hubble times, the universe is actually being dominated by something very close to a cosmological constant. I'll get back to that in a second. So that means that now if you put these things together, okay, still not using Einstein equations, just using conservation laws, now you should see that we know there are photons in the universe, so those dilutes as 1 over a to the 4th. Sorry, radiation here. There is matter in the universe that dilutes as 1 over a cubed, and then there may be something like this cosmological constant, which doesn't dilute. And so in case it's not obvious, what I'm plotting here is a log-log plot of density, energy density as a function of scale factor. So as the universe expands, you can see radiation dilutes faster than matter, which dilutes faster as cosmological constant. So that means naturally, okay, these arguments don't tell you the relative amplitudes between these curves, right? That only can be set by observations. And observations said that this transition here and this transition here, we are here today. So this is A equals to 1. This transition when the universe underwent from matter dominated. So you can see in this era here, matter is the most important component. We call that a matter-dominated universe. Earlier than that, we have a radiation-dominated universe. And here we have a lambda-dominated universe. Observations tell us that this point where the universe once went from matter to lambda-dominated is about a scale factor of roughly 1/2. And the transition from radiation to matter-dominated happens at roughly 10 to the -3, or 3 times 10 to the -4, to be more precise. So we have at early times radiation-dominated and matter-dominated, and something that looks like a cosmological constant-dominated universe. Now, how do we know about this? We know about this because of the acceleration of the universe that was discovered in 1998, so I'm going to get to that in a second. And I will finish essentially all the properties of the smooth universe that we need for our discussion of structure formation. So now finally, we get to the equations of general relativity for this particular metric, okay? And so the first equation, there are only two independent equations, okay? So one is the time-time part of the Einstein equations, which Friedman was the first to write, so it's known as the Friedman equation. In fact, the other one is also a Friedman equation, but somehow this one is only the one that people often refer to as the Friedman equation. And so you can see it tells that the expansion rate of the universe is related to how much energy density you have. And then there is a term here that describes that depends on the spatial curvature. Okay, so K, remember, can be +1, -1, or 0. And we can write this equation in a slightly different form, which it's very useful for understanding all the plots that people make about cosmology all the time. So we can rewrite this equation as in terms of what is the spatial curvature that you get depending on the density, okay? And you can see here, there is this quantity here is a characteristic density. When rho is equal to this, the right-hand side is 0, and we have a spatially flat universe. So this characteristic density is what we call the critical density. So it's the density that you need to have to be spatially flat. Okay? And if you put the value of the present Hubble constant, then today, this corresponds to roughly 5 hydrogen atoms per cubic meter. Okay, you can do the calculation. Just plug in this thing, plug in Newton's constant, G, and then you will get that the density to make the universe spatially flat is only 5 hydrogen atoms in a cubic meter. Okay? That's a crazy low density. In fact, it's so low, no laboratory on Earth gets even close to this. Okay, so in cosmology, then we usually scale out the density by the critical density and define what we call omega. So this is just a dimensionless parameter, omega. And thought here is to emphasize this is total, so there are many contributions to the energy density, say, non-relativistic matter, radiation, neutrinos, all the particles that we have, okay? And so you can write this as a sum over all components in the universe, and each of them will have its omega, okay? So we will have omega matter, omega radiation, and these are functions of time. Okay, and one of the main jobs of a cosmologist is to figure out what are all these numbers, what are the constituents that source the expansion of the universe. Now, if you write, since we wrote this in this way, right, this is just omega total minus 1. Some people like to define the curvature as think of it as another contribution to the energy density. So we can define this thing as minus omega curvature. That's just a definition with little physical meaning. It's just a mathematical definition of getting the curvature in the same units as the rest of the components. So you can see then that always the total omega plus the curvature omega is equal to 1. Okay, that's just by definition. And now here comes the important part. So you can see this curvature omega will depend on A in such a way that now if I calculate what is this density, right, its density will be omega curvature times rho critical that goes as Hubble square. So if I multiply this by Hubble square, the omega curvature dilutes as 1 over A square. So you can think it as curvature as another contribution that now dilutes as 1 over A square. And this is important for considerations of the flatness problem and so on, which you probably hear about from Gonzalo when he talks about inflation. Now, the interesting thing is that today we can constrain. So if I put time today, so I'm putting a 0 there, we constrain this extremely well from the physics of the microwave background that you will hear about next week. We know the universe is very close to spatially flat, as I advertised earlier, and the way the constraints work is in terms of this omega. So we know that today, from looking at the microwave background, the omega curvature is less than 4 times 10 to the minus 3. Okay, so this is the extent to which we know the universe is spatially flat. Okay, so that's what I'm going to take from now on, the case that we live in a spatially flat universe, but there is a very good reason from observations from that. Okay, so now, given the Friedman equation, given this equation, if I set k equals to 0, if you give me rho, I can solve this differential equation for A as a function of time. Okay? So now I'm going to put a critical density worth of radiation and solve for A of t, a critical density worth of matter and solve for A of t, and then a critical density worth of a cosmological constant and solve for A of t. And so if you have rho matter equal rho critical, okay, so omega matter equal to 1, then again, this is an exercise for you guys to derive. Very simple differential equation. So the scale factor evolves as t to the 2/3 if we are matter dominated. If we are radiation dominated, then the scale factor is t to the 1/2. And if we are lambda dominated, the universe expands exponential. And exponentially, the exponential time constant is 1 over the Hubble constant, which in that case is truly a constant. Okay? So if we have k equals 0 and rho doesn't dilute because we have a cosmological constant, the Hubble constant doesn't depend on time either. So in that case, it's truly a constant. And so you can see in each of these eras, the universe is expanding as a power law, radiation and matter dominated, and now we are entering, in recent times, exponentially expanding universe. Now, there are two independent Einstein equations. The other equation is the spatial part of the Einstein equations. And that's the most physical way of writing that equation is to look at the trace reverse Einstein equations, which describe the tidal field. Okay, the same thing you have in Newton's case, which describes accelerations. And that's the so-called acceleration equation. And that tells you that acceleration, so the first equation describes the speed of the expansion of the universe. This one describes the acceleration of the expansion of the universe. And you can see here there is a very important minus sign. And up to these constants, the thing that drives acceleration is this combination of rho, the density, plus 3 times the pressure. Okay? And remember, if you put back the units, here it will be a c squared here. So this is what in general relativity is called the active mass. So in GR, not only density sources gravity, but also pressure, because density and pressure are related by Lorentz transformations. They are fluxes of constant time and constant coordinates. Okay? And in GR, you can move this around, and so you cannot distinguish between the two. The two have to be sources at the same time, and because there are 3 spatial dimensions, pressure comes with the 3. And so you can see now that if I put my equation of state, the acceleration of the universe is proportional to the sign is proportional to minus 1 plus 3W. So you can see going back here, when we are dominated by radiation, 1 plus 3W is positive, so the universe is decelerating. When we go into matter-dominated era, 1 plus 3W is still positive, so the universe is still decelerating. But when we transition to an omega equals minus 1, you can see there is a change of sign here. This becomes minus 2, so this is plus 2, so the universe now accelerates. Okay? So we go from a decelerating universe to an accelerating universe. Okay? And in order to have acceleration, you need to be dominated by a component which has an equation of state with W more negative than minus a third. And of course, the cosmological constant satisfies that. So anything that drives acceleration, we call dark energy. So a big enterprise of cosmology is to figure out what is the thing that is sourcing this acceleration of the universe that we observe. And current observations are very close to constraining W to be very close to a cosmological constant. Okay? So that's what I'm going to assume from now on. I have a universe which is spatially flat and dominated by a cosmological constant. Today, the values of the cosmological parameters, we live in a universe which is spatially flat, so the sum of all these omegas must add up to 1. Roughly 30% is in matter, which is baryons, all the particles in the standard model, and some mysterious component that we call dark matter. And this is roughly 0.04 to 0.05. This is 0.25, roughly. So this is about 5 times as more dark matter than baryons. So these particles or these contributions, we don't know exactly what they are. We just detect them through their impact on the expansion of the universe and structure formation, as we'll discuss. And so we have a universe which is, its matter content is dominated by dark matter, and there is nowadays an extra component, which is about 70%, which is this dark energy very close to a cosmological constant that is making the universe accelerate. Okay, so that sort of summarizes the smooth universe. Are there any questions about this? I went fast because this is just the background that I assume most of you have seen this, but otherwise you can read my notes. They are in more detail than what I just said. Okay, and I'll give you also links to my website my courses where there are even more expansion about this discussion here. Okay, so that's the description of the smooth universe. Okay, so now we are going to transition to the real subject of my lectures, which is, okay, we know the universe is not perfectly smooth, and now we want to describe fluctuations. Okay? And so in order to describe fluctuations, before I get into the actual equations of motion and initial conditions that describe fluctuations, I need to put everybody on the same page of what are the techniques of statistical physics that we're going to use to describe fluctuations. Okay? And why do we need statistics? In particular, we need to develop some understanding of what is known as random fields. Okay? And so the idea, this goes as follows. Okay? So when you have a physical system in the lab, right, what you do some experiment, you have some physical system, you have great advantages with respect to a cosmologist. Okay? You probably get paid more. That's one advantage. The second advantage is that, very crucial, you are building your physical system, and you can build multiple copies of them, right? And you can average over many realizations of your experiment. Okay? So for example, when LHC, this accelerator, runs all these, do all these runs and builds up statistics, what it's doing is repeating the same experiment over and over again and averaging the noise out and building statistics. Okay? Cosmologists, we don't have that option. There is only one universe. Okay? And if you think about it, it's pretty amazing what we are doing, right? The universe was born, 15 or 13.8 billion years ago. It was developing all this structure along the way, as we'll discuss. Suddenly, this civilization gets formed in the planet Earth. Eventually, we get to develop telescopes, and we just point to the sky, and these photons that have been traveling billions of years, we catch them, and we try to figure out what the hell was going on in the last 15 billion years, okay? And you only have one chance, one universe, no more, okay? So in particular, the way this structure developed, as Gonzalo is going to describe in detail, and I'm going to mention a little bit more, we think these fluctuations that we see in the universe are the outcome of quantum fluctuations when the universe was very, very young and very, very small, okay? So there is one story here that I'm leaving out, which is there is another period of the universe at very, very early times, okay? A very small fraction of a second, when the scale factor was like 10 to the minus 30, whatever, or more, what is today, where the universe was doing the same thing that it's doing today, expanding exponentially. And during that time, the universe is so small. In other words, the Hubble radius is so tiny that it's microscopically small. And quantum mechanics, you cannot have a perfectly smooth universe in quantum mechanics. Naturally, because of the uncertainty principle, you will have fluctuations. And what we think is that those fluctuations, when the universe was expanding exponentially, you can show it stretched to macroscopic scales. And those are the seeds for the structure of the universe we see today. Now, there is absolutely no way of predicting, is this location of the universe going to have higher density than the average, lower density than the average, or what? We can only predict the outcome of this process statistically, okay? And so that's why we build the concept of a random field. A random field is, you have, like in statistics, you have a random variable that is fluctuating, and a field is something that varies at each point in space, okay? So we are going to have, at each location in space, we are going to have some field, okay? And let's fix time. And different components are going to have some constant background, which will be what describes the smooth universe. And then it's going to have some fluctuations on top of it, okay? So I'm doing my best to draw a random field, is something that is not completely crazy, despite my drawing, okay? There are correlations between neighboring points, and correlations will decay with distance in some very specific manner, okay? So that's what we're gonna study. And again, the reason we have to do this is because in cosmology, we don't predict what are the physical properties of the universe. We cannot predict what will be at each specific point in the sky. We can only predict statistical averages, okay? And so, so a random field is a random variable at each point. In space. And what we are going to do, and this is the connection to the smooth universe, we are going to have some random field, which could be, say, the temperature, could be the density, magnetic field, whatever physical property we are interested in. Okay, so I'm going to call it phi now in general. Then we'll get to, and we are gonna, so at each time, okay, so I'm going to put time for a minute. We're going to decompose this into the mean and then a fluctuation. Okay, so this is the statistical mean, and this is the fluctuation. Okay? And so the mean is going to be this overall level at a given moment of time. That will be, say, the matter density, okay, at a given time. And then fluctuations about it, because the universe is not perfectly smooth. So this describes the smooth universe that we just went through. And then on top of that, we will have fluctuations, okay? And now here comes the trick, okay? So this mean is going to be some function of time alone. And why, I'll tell you in a second. Okay, so averaging, if you were able to average over many universes, this thing will come out to be only as a function of time. And that indeed is what sources the smooth universe. And then on top of that, we will have the fluctuations, okay? So I'll go over why that makes sense in a second. It may not be obvious that this is only a function of time. And so, so what we mean by these angle brackets that I put there is, and as in probability and statistics, so the average of a random variable x is its integral over its probability distribution function. So this is the PDF. Okay, so that's a statistical average. So you have to know what is the statistical probability distribution function for any random field. So for example, from inflation, we know, as we'll discuss in a second, well, maybe, I'm not sure I'm going to get to it today, but maybe tomorrow, the observations constrain this probability distribution function to be very, very close to a Gaussian distribution, which I'm going to define in a few minutes. And so we know what these functions are, or at least we have constraints on just from observations. Sometimes the physics of it already tells you if it's likely to be a Gaussian distribution or non-Gaussian and so on. We'll get into details of that quite a bit later, okay? So, so in cosmology, we usually work with dimensionless fluctuations. So we take the fluctuation and we divide by the mean. And we do that for a lot of things, like the temperature of the CMB fluctuations, the matter fluctuations, and so on. So this is what we'll call the dimensionless fluctuations. Sorry. let me, before I do that, let me do it this way. Okay, sorry. Let me do it this way. So let me first do that thing. Okay, so we are going to define dimensionless fluctuations delta sub phi Okay, so examples are the matter fluctuation, which will be raw matter minus its average divided by the average, the same for the CMB temperature and so on. Okay? Now, the reason for that, among other things, is to make it dimensionless and to get rid of the mean, which is something trivial, okay? Because that's the mean is just taken care of by the smooth universe part of the equations of motion, as we'll see later. So it's a nice way of working with fluctuations. And so if I look at here now, back to my crazy drawing of a random field, right? This is the average, okay? So this is phi bar. So at each point in space, I have a delta phi, which is whether I'm above the mean or below the mean. Okay, so that's my delta phi. So these yellow arrows describes the fluctuations away from the mean, and then to normalize it, I divide by the mean itself. Okay? So, so now let me get back to this idea, why this mean will describe just a function of time. And as I said, this goes back to the idea that we only have a single universe. Okay? So ideally, what this means, if you have many universes, this mean will be taking different universes, making measurements, and averaging over all of them will build this mean field, okay? Which is what you do in the lab, right? In the lab, you build different realizations of your experimental setting, okay? The LHC example I was giving, averages over many copies of it to reduce noise. We don't have that in cosmology. So what we do is we replace this by something that we call ergodic hypothesis. And it's very clear, this is an assumption, okay? Without this assumption, essentially we cannot do cosmology, okay? At least at very large scales. And the idea is that these expectation values over the ensemble, they equal spatial averages. Okay, so that means, in particular, for the mean of the field, to give one particular example, okay, so that will be the thing you will have to do is to run many realizations of your experiment and average, okay, which is equivalent to average over its probability distribution. We say, because of ergodicity, this is the same as averaging over space. Over some very, very large volume, the universe's volume. And this, of course, you can see will be only a function of time. Now you may ask yourself, wait a minute, this sounds like a very strong assumption. And at face value, it is a strong assumption. But as I said, we don't have much options. We only have one universe. So the question is, what do we know about random fields that make this ergodicity assumption work? And you can show that ergodicity works, or you can prove this ergodicity theorem for homogeneous, statistically homogeneous random fields. with a continuous power spectrum. Sorry. Statistically homogeneous Gaussian random fields. Okay, so I still haven't defined. We defined what homogeneous is. We didn't define what statistically homogeneous is, which I'll do in a second. We defined what a random field is. I didn't define what a Gaussian random field. I will do it in a second. And I didn't define yet what the power spectrum is, but I'll define it in a second, okay? But we have the conditions under which this assumption holds, and everything we know about the universe is consistent so far with these three key properties, that the fluctuations that we have are consistent with having primordial fluctuations, which were statistically homogeneous, Gaussian, and with a continuous power spectrum, okay? So if we ever derive, or we ever constrain something that doesn't obey this, we have to do some work, okay? Now notice this doesn't mean that, for example, primordial non-Gaussianity is forbidden by this, because you can always have the primordial non-Gaussianity in the early universe being the outcome of some process on a Gaussian field, okay? So if there is some underlying Gaussian field that is the source of everything, we are still okay, as long as it's statistically homogeneous with a continuous power spectrum, okay? So I had to define these three things now. Let's see if we can get to that. But this is, at the heart of everything we do in cosmology. So when people measure, say, the temperature of the CMB, okay, the mean is obvious, you average over the whole sky, right? And then you measure the fluctuations. You only have one CMB sky. So basically, you are doing correlation functions, okay, on the sky, averaging over the CMB map. And when we do galaxy clustering, we average over space, okay? And we equal this average over space to averages over the statistical ensemble. So this is actually how we make all the measurements in cosmology, okay? Everything. Okay, so now let's get into the statistical way we describe the universe, right? As I said, in cosmology, we cannot predict where here we will be above the mean and here we will be below the mean, okay? So we measure this crazy field, right? But then we build statistical objects, which are these correlation functions, by doing spatial averages, okay? And so those will be deterministic functions of space and time, okay? They will not have these crazy variations that the fields have from point to point. And those are the things that we predict for the fluctuating universe. So when we are testing theories, this is what we are doing. We are building these correlation functions through observationally through these spatial averages, and theoretically we are calculating these correlation functions and we are testing against observations, okay? That's the arena where cosmology of the fluctuating universe works, okay? So what are these correlation functions? As the name implies, what we are now asking is not what is the value of the field at each particular location, but what are the correlations between this point and this point, okay? If this point is high compared to the mean, is it more likely that this other point will be high or will be low? These are the kind of questions that we are asking, okay? How these 2 points are correlated. And what happens if I now increase the distance between these 2 points? Is this point with this point more correlated or less correlated if I'm here? As you can imagine from the setting of the universe being homogeneous and isotropic at large scales, the idea is that as the two points get farther and farther away, the correlation with them disappears, okay? And this is the same that happens for basically any physical system, okay? For example, the temperature of this room, if there is a heater over there, if you put a thermometer there, the temperature will be high. If you put it very close to it, it will still be high, but because the heat has trouble propagating, okay? If I put it very, very far away, I go out this room, eventually the temperature will decay, and the fact that here is high doesn't tell me that much about what's going on at a very far separated point, okay? And this is how the weather works, right? If it's raining here, okay, so if you are close, it may be raining, but as you propagate, as you move away from Sao Paulo, eventually you will get to a sunny place, okay? And there are no correlations. Okay, so this is now what we are going to do. We are going to build, instead of just one-point functions, averages of the field at some particular location, we are going to include more functions. So now I'm going to work with these fluctuations of some physical quantity. Okay, I'm not specifying what phi is. Phi could be the temperature, the density. So this will be the two-point function, because there are 2 points, x1 and x2. You can build the three-point function. And you can go crazy, build all the n-point functions for arbitrary n. So you will have n fields. And all the statistical properties of a random field get completely specified once you specify the n-point functions with n going to infinity, okay? That's a very tough job to do. Typically, when people do this in observations, we work with the 2, 3, and 4-point functions. That's the current status, okay? It's also possible to build other statistical measures which are combinations of all the n-point functions, okay, which are some other type of statistics, which I'm not going to get to in these lectures. So this is what we want to measure and predict. So let me now start to get into some of these ideas that I owe you, okay? And for that, now let's discuss symmetries again. So we discuss symmetries for the smooth universe, homogeneity and anisotropy. Now let's discuss the symmetries of the fluctuating universe. Now if you look at this, you say, what the hell is this guy talking about, right? This is variating and it's changing all over the place, right? What kind of symmetries will you see here, right? Of course, if I look at this with my eye, when I was a student, I don't see anything, but now I see it, okay? So my hope is by the end of my lectures, if I draw you a random field, you will be able to tell me, oh, this field is probably very likely Gaussian. It probably has a power spectrum that increases with k or decreases with k. This is my job, okay, to make you experts about this by the end of my lectures, okay? So what I claim is that there are some regularities that I'm drawing here, okay, and those are picked up by these correlation functions. And in particular, we have symmetries also at the level of the fluctuations, okay? And these are natural extensions of the idea of homogeneity and isotropy that we have at the level of the smooth universe, but now extended to the fluctuating universe. And that arises as now descriptions of whether these deterministic functions of space and time are statistically, now we say statistically because there is a statistical average, homogeneous functions and isotropic functions, okay? So that's the idea. So we now say a random field is statistically homogeneous if its correlation functions are invariant under translations. So notice now, same thing that we talked about for the smooth universe at the level of the field. Now that's out of the window. We have fluctuations. So the field itself is not statistically homogeneous, right? Because if I'm here at this point, my temperature is high. If I'm here at this point, I did a translation, okay, by this distance. Now it's different. So homogeneous is not. But statistically homogeneous now means that the correlation functions are invariant under translations. Okay? Not the field itself, but the correlation functions. Okay? So let's see what this means. And as usual, when you have a symmetry, you have a lot to gain. That's the lesson of physics. Symmetries means good news. Okay? Things are about to get easier. Okay? So let's see how this works out. Okay? So suppose I'm measuring some horrible endpoint function. Let me drop the time argument because it's not relevant for this discussion, right? We are only arguing about at fixed time. If this correlation function now, if the field is statistically homogeneous, means this correlation function is invariant under translations, which means I can shift my coordinates by any amount, and I recalculate this, I get exactly the same answer, okay? So that means it cannot depend on all the coordinates by themselves. It can only depend on the relative coordinates, because I have to cancel a translation, okay? So this means that this has to be a function of relative coordinates. So let me define xij to be xi minus xj. So this is not a function of x1 alone, x2 alone, and xn alone. If it's a statistically translation invariant, depends on the relative coordinate from 2 to 1. Let's choose 1 as a reference point, the relative coordinate of 3 to 1, and so on. Okay, is that clear? Okay, so it depends only on relative coordinates. Okay, so that's what statistical homogeneity means. And I'm going to give you some particular examples in a second. So if I now do a translation where I change everybody by some arbitrary vector lambda, obviously this function f doesn't change, right? And that's now the notion of homogeneity, now extended to the properties of a random field. Okay? Next thing, we do the same with homogeneity. Now we say whether statistical field is statistically isotropic. Same thing means that correlation functions are invariant under rotations. Okay? So that's what we mean by statistical isotropy. Okay? So this is something that, again, you can test observationally. So far, we have no evidence that there are deviations of statistical isotropy and statistical homogeneity. As we'll see when we go to the very end of my last lecture, when we discuss Redshift space distortions, we will see these properties may be broken just by the way we make observations. Nothing about physics. It's just our limited way in which we make observations. So we'll discuss on Friday that there are some fields that we observe which are statistically anisotropic. There also could be statistically inhomogeneous, but this we understand. It's just the way we make observations. It has nothing to do with the physics. Everything we know about the physics of the universe is that there is no special place in the universe, there is no special direction, and the properties of statistical homogeneity and statistical isotropy is how we mathematically test that, okay? Good. So let's see now how this symmetry buys us some interesting thing. So let's consider the two-point function in 3 dimensions, which is what we live on for now. So if I look at the, again, phi some property. So in general, right, the two-point function is denoted by the letter psi, the Greek letter psi. In general, if there are no symmetries, this is a function of 6 variables, right? Because we have 2 vectors in 3 dimensions. So if there is no statistical homogeneity and isotropy, that's a function of 6 variables, okay? Now if my field is statistically homogeneous, I'm invariant under translations. This becomes only a function of the relative coordinate. And you can see automatically I halve the number of variables that I need to describe my two-point function. Big, big saving there, okay? Finally, if I can make the assumption that my random field is statistically isotropic on top of homogeneous, it cannot depend on the vector, right? Because it will depend on the direction. That breaks statistical isotropy. So it can only depend on the magnitude of this vector. And now you can see we end up with a function of a single variable. So I went down by a factor of 6 by using these symmetries, okay? Let's do one more point function, and then we can see the same thing. So now suppose I do the 3-point function. Okay, in general, this will be 9 variables, so it will be some function in 3 dimensions. You can see how it can be pretty horrible, right? Now, if I have statistical homogeneity now, I have invariance under translation. This depends only on some function, zeta, another Greek letter. Now of the 2 relative coordinates, okay? So now this depends on, in general, will depend on 6 variables. Okay? And finally, if I can assume statistical isotropy, then it can depend only on the relative lengths that I can form with 3 points. So what are the lengths? If I have 3 points, I have, so this is point 1, point 2, and point 3. Now I have 3 lengths that I can form. And this becomes just a function of 3 lengths. Let's call it, this length will be x21, this will be x32, and this will be x31, okay? What are the lengths that you can make out of 2 vectors? You can make these 3 lengths, which are the size of a triangle. So this will be x21, x31, and x32. So again, you can see I went down from 9 variables to 3 variables, okay? And what this is saying now, you can see that if I can make these assumptions, this also will make possible measuring things in observations very easily. So suppose I want to measure the two-point function on the sky, okay, for galaxies or for the CMB. What I need to build is, if I'm statistically isotropic and homogeneous, is a function of the relative separation between 2 points. That means if I fix the distance between my 2 points here, right, this, they are all statistically equivalent. So I can just average over all this. As long as I keep in my vector the same length, and in any directions, because I'm statistically isotropic, I can just average all of them. This is how we measure things, okay? Same thing for the 3-point function. You would just put a triangle on the sky and just move it around and rotate it any way you want, as long as you keep the shape of the triangle the same, and you just average over all of them. All right, so I'll stop here. Tomorrow we'll see how we can take advantage of these symmetries by going to Fourier space. We will see things get a lot easier if we do a Fourier transform.
So questions for Roman? Wait for the microphone, okay? Because we are recording this. Any questions? Yes, just a second.
Thank you, Roman. I have a question related to the correlation functions. So what happens if you take this n to be very large? I mean, what do you obtain? Do you obtain like the whole picture or something? Or?
Yeah, so the idea is that in order to describe fully the statistical properties of any random field, you need the infinite hierarchy, okay?
Yeah.
Now, obviously, that gets very inefficient. So that's what I said. Typically, when we measure these things, we basically measure up to the 4-point function, okay? Now, as it turns out, we will see that once we look at the physics, there is a reason why actually capturing the first few endpoint functions is enough to describe most of the physics. So it will have to do, this will have to do with the fact what is the physics of structure formation? What kind of nonlinearities, what kind of non-Gaussianities will get generated by your physics, okay? Yeah. If you are at large scales, as we'll discuss later, you will see that the information encoded in each endpoint functions, it decreases as you increase in n, okay? So this will depend on the physics that you have at hand, okay? As I said, also, there are other statistical properties that you can build, for example, topological properties of the random field that depend on all the infinite hierarchy of endpoint functions. So that's another way of testing whether there is information in the 57th endpoint function that you're not measuring by measure some other statistic that depends on all of them. Yeah. And we have such statistics as well. Yeah.
Okay, thanks.
I wanted to ask a question to clarify one point. So here, when you use this, a lot of conditions here to be able to use the ergodic hypothesis, this statistical homogeneity and isotropy is independent from the fact that the field can be Gaussian or not. So you can use these symmetries even today even if you have non-Gaussianities in the field, you can still use these symmetries to make
these symmetries have nothing to do with Gaussianity, which I still haven't defined. Sorry, I will do tomorrow, okay? And I haven't defined what is the power spectrum, so we're getting there, okay? So I just defined this, yeah. This is completely independent whether the field is Gaussian or not, yeah.
I'm just a little bit confused about the notation. Where is like the mean symbol and where is the vector symbol?
The vector symbol for the coordinates?
Yeah, yes.
Sorry,
this is vector. These are vectors, yes, and the fields are mean.
Oh, sorry, I'm a horrible professor.
No, not at all.
This is not a vector, yes, sorry.
Okay.
Yeah, cosmologists will use crazy notation all the time. Sorry, a bar, this is a bar. This is supposed to be an arrow. Sorry, this is supposed to be an arrow, but I'm lazy to draw the...
Yes, that's what I imagined. Just wanted to be
Good, very
certified.
good
Thank
question.
you.
Very good question, because I'm sure, you know, when I teach this, everybody's asking me that question all the time. And sometimes I draw the arrow, then I forget it, and is this the same? I do all the kinds of things like this, so I'm sorry, yeah. But, yeah.
Some more questions? Yes.
Hi, so first, thanks for the lecture. So you were saying that the ergodic hypothesis is true if your random field is statistically homogeneous, is Gaussian, and has a continuous power spectrum. For instance, the matter distribution, it begins Gaussian from inflation, but then it evolves under GR, and now I think it's very non-Gaussian. So
Yeah.
I imagine that like this deterministic evolution doesn't break the ergodic hypothesis. But are there any processes that could break this hypothesis?
Yeah, that's exactly the point. So you will see when we do calculations, right? We calculate explicitly something that is non-Gaussian. It's still statistically homogeneous, as we'll discuss, okay? And we still have a continuous power spectrum, but the Gaussianity is going to be broken by the nonlinear physics. Once you have nonlinear physics, Gaussianity is out of the window, okay? However, the way we do calculations is because we have equations of motion, we can relate it to the underlying Gaussian field. And that's where the statistical averaging is being done. That's the only part that is not deterministic. Everything else is deterministic and comes out of any expectation value that I'm calculating. Okay? So that's key number one. Now, suppose you have something that is some physical process that is discontinuous. You can have shocks, you can have some crazy things. Then you have to be careful, yes. Also, suppose you want to describe what happens inside the galaxy, right? Then you cannot use the concept of statistical homogeneity because there is a special place which is the center of the galaxy, right? The galaxy will not. So in cosmology, of course, we are looking at much, much larger distances where we have large volumes. So yes, you have to be careful how you do this, but so far we are okay, okay? And even if you have non-Gaussianities during inflation, typically you can relate them to a Gaussian field with a continuous power spectrum. It's interesting to actually find deviations from this, and some things years from now maybe discover that will break this, but so far, yeah, we are okay.
Yes.
So could you look for any point functions for different fields?
Yes.
And what information would you get from it?
Yeah, so we will see there are different probes of how the structure forms. For example, the simplest one will be the clustering of galaxies, the endpoint functions of galaxy positions on the sky, right? So that will be one particular set of endpoint functions. The other one, I was saying, the temperature of the CMB has small fluctuations. We can measure the endpoint functions there. We can look at gravitational lensing, for example, and you will build maps of gravitational lensing, say the convergence, as I'll mention later. You can also build, you can build endpoint functions about anything, any probe of structure. Okay, the Lyman alpha forest, we can measure, say, the hydrogen, neutral hydrogen fluctuations. Yeah, lots of different things. Yeah, so and that will give you different endpoint functions, and we have constraints on all of them, whether they are underlining the same fluctuations coming from inflation are causing all of them. And so far, everything is consistent with all being sourced by the same underlying power spectrum, which we'll discuss tomorrow. Eventually, I will show you nice pictures about all these constraints. Sorry, my lectures are a bit dry now, no pictures, nothing, but we'll get there, okay?
Hey, thanks for the lecture. I just wanted to know if my survey does not have a large area, this symmetry still hold? Can I still use it? Or
Yeah, you
not?
have to be careful. If your survey, if you have a very small volume, right? I mean, the answer is it depends. So this is always the worst answer you can give, but it's true, unfortunately. Typically, once people release data or release analysis, means that they collected enough volume so that these assumptions are pretty good. You can also correct for deviations, because if your survey has a funny shape, there are corrections you can make using random catalogs and things to account for this, which maybe we'll get to towards the end, but yes. Yeah.
More questions? So I have a very quick question, but it's the opposite direction of what she was asking. Maybe we can discuss this in the Q&A. And people go to sometimes people discuss field-based inference methods. So it's one-point functions, let's say, no?
Yeah.
So whether or not this is useful, I think we can discuss this later on a Q&A. I think this next week, probably there will be some talks about field-based inference.
But yeah, probably for that, we need to wait a couple more days until I develop this a bit better so I can explain.
Very good, very good. Okay, so let's thank Roman again for this very nice reaction.